Well, happy September, everybody, and welcome to this month's Mozzie Tech Talk. We're going to be talking about cost savings for GPUs. It's a topic that's actually started coming up a lot over the course of the summer. I've seen it on a number of different online communities, questions about how do you save money on GPU costs, particularly when you're running machine learning models in production and actually using these models to make predictions at scale. It can be expensive, it can be hard to understand how to keep these costs low, and the bills can be really enormous. So we're going to talk today about some different things that you can do architecturally, some things that you can do physically to try and cut your costs overall. And I'm really excited to have this talk because it's been such an area of interest for the community over the past few months, and hopefully you'll find some of these tips and tricks useful and helpful. So let me go ahead and share my screen here and we'll get started. All right, and here we go. So I've seen these quotes pop up in a couple of different communities that the Mozzie team is involved with, wondering about how other folks are managing their GPU inference costs, how to take advantage of idle GPUs, how to make sure there's as little downtime as possible. And it's not always obvious. There's a lot of different ways to do machine learning, but one of the unfortunate truths is that the hardware can be expensive. So let's get started with some basics and some background information. There's two major phases within the machine learning ecosystem when you're using GPUs. One is during model training, and then the other is during model inference. Model training, we're not going to talk as much about that today. That tends to be pretty complex to reduce costs. It's time intensive, it's expensive, it does take time. The nice part about model training, though, is that it's not something that's done every single day. The training process is completed, ideally, after some iteration, and once you get that model, you're going to start using it against real live data. That is where we can really do a lot more of our cost savings efforts, is after you've trained a model and you're ready to start actually using it. So some general advice, a few tips on saving money when you're using GPUs. So the first is try using a CPU. It's an underrated piece of hardware for a lot of use cases, particularly if you don't have really high latency requirements. But increasingly with Intel's newer architecture, Cascade Lake, along with some clever model architecture selection, automation, quantization of models, you can get surprisingly good performance on a CPU, even for deep neural networks, which are typically the type of architecture that tend to go along with GPUs. GPUs and neural networks are tightly linked, tightly coupled, but you can actually do quite good work on a CPU if model latency isn't the most important metric. Another tip is you might consider building your own GPU server. So cloud providers have to add a markup, obviously, to all of the infrastructure and instances that they make available. As an example, I just did a cost comparison for AWS's what they call their G4DN 8x large, it's a mouthful, GPU instance. Essentially, that's one of NVIDIA's T4 GPUs on a server with, I think, about 196 cores and maybe a couple hundred gigs of RAM. When you cost that out to run a model on AWS's infrastructure 24/7 for a year, it's around $19,000. If you were to purchase a physical server with roughly the same specifications, you could purchase that entire server for about $15,000. Now, that's a capital expense, whereas cloud hosting is an operational expense. For the financial folks on the call or listening in, those do matter, and there are reasons why you sometimes want to have higher OpEx than CapEx. But once you start scaling this up and running production instances for multiple years, provided you have the infrastructure to actually cool and power your servers, it can be a pretty significant savings. So if you're starting to use your models pretty regularly and you're getting really high utilization and your instances on AWS or Azure are running near constant, try consider building your own server. You may find a real savings there. And then third, just generally speaking, try to make sure you're using the GPU as efficiently as you can. One of the benefits of using a GPU is that they do parallel processing really well. Just the nature and the structure of the processing units mean that they can do multiple functions at the same time. That's actually how they process inputs. They're taking in, let's say, every single pixel of an image as a different element in an array, and then that array is passing through a forward feed neural network in a GPU. But GPUs can process actually multiple inputs through the same neural network simultaneously. So that can be a huge cost savings. That's one of the reasons why you would want to use a GPU, in fact. But don't let that go to waste. Don't be sending one input at a time through the hardware. Make sure that you're adjusting and setting the batch size so that you're able to process as many of those inputs through the model at a time as your model and your hardware will support, which requires a little bit of experimentation, but if you can get it just right, it's a huge time savings, because then you can process all of your inputs faster and then turn the GPU off when you're done. Now, if you're committed to the cloud, you can still save on GPU costs. So there's a couple of things to look at. One is reserved instances. These are available on both AWS as well as Azure. And depending on the type of instance and what region you're in, each of the cloud providers have different costs in different regions. You can save anywhere from 40 to 70% if you're willing to make basically a 1-year commitment up front. Not a great option if you're doing research and development, if you're doing prototyping, but if you have a model that you know is going to be used within a production environment, or even you have plans to start deploying models and new versions of models in a production environment over the course of the next year. 40 to 70% savings, that's significant enough where it could be worth making that investment. However, you obviously don't have the flexibility of being able to turn those instances off, so there's a risk. And then another sort of type of flexible option you could take advantage of are spot instances. And there's a spot market, it's variable, it's flexible. You don't always know what's going to be available, but if you are able to take advantage of them and you're able to architect kind of your platform to consume those spot instances when they become available, you could save up to 90% of the costs for particularly batch ML jobs. Because of the nature of the spot market, you can't guarantee that you're always going to be able to get the infrastructure that you want at the speed that you want. So it's particularly useful if you're doing batch processing as opposed to real-time or streaming processing. All right, now we've talked about some general things that you can do to save GPU costs. The next level of cost savings really comes down to architectural decisions that you may or may not need to make for your application, for the scenario in which you're operating in. So we're going to look at a couple different scenarios. One scenario is batch processing with a single model. The second scenario is real-time or streaming with a single model. What kind of architectural decisions you might make there. And then finally, what if you have a need to provide both batch and real-time processing with multiple models? How might you make some architectural decisions to again, save those GPU costs? Well, here's one really simple architecture, maybe the simplest architecture that you could architect, that you could design in order to keep the GPU time as low as possible. So one would be to manually launch a GPU, and on that GPU within the cloud, host your model service. One of the simplest ways to do that would be to take your model and wrap it with Fast API, which is essentially an API service that will turn your machine learning model into its own service, and does so relatively quickly, hence the name Fast API. So with Fast API plus some Python code and an AWS account, you can actually create the service pretty simply. At that point, process your data for batch processing through that model service, and then as soon as you're done, manually shut the GPU down. So kind of the key elements here for batch processing is that you want to get as high of GPU utilization as you can. So just pack that thing full of data, constantly submitting data through the GPU to get as close to as 100% utilization as you can get. And then as soon as you're done, turn it off. That is really going to basically pack in the value you can get for the amount of money that you're paying. Now, A slightly more complicated but more elegant solution would be to introduce the concept of a queue. So in this scenario, what you can do is create a queue, and then you would submit your batch inference jobs to that queue, basically saying, hey, here's a bunch of data. Here's maybe a giant folder of data in S3 or a file server, and I want to send all of this data through my model. Add that to the queue, and then you can create a small service that just watches that queue. And as soon as that queue has any jobs on it, that service, that small little code, can then dynamically spin up a piece of hardware. This would typically be in the cloud, AWS or Azure, or Google Cloud if that's your cloud provider of choice. And then again host that model service. Here we'll again have a machine learning model that's just wrapped with the Fast API. And finally, once the queue is empty, once this queue has been drained of all its jobs, you can then shut the GPU down. And again, you get that scale to zero boost, which is a really effective architecture sort of design for batch processing, because it automatically shuts down the GPUs as soon as the queue is empty. So this takes a little bit more work, a little more planning and testing, but it's not manual, which is really nice. It means that you won't accidentally forget to turn a GPU off after you're done with your process. Now, in the scenario of real-time and streaming, we have some different challenges. With batch processing, there tend not to be as many concerns around service level agreements, basically inference requirements for how fast the model needs to return its result. So there's some trade-offs you have to look at. One is that spinning up new GPU instances takes time. So in a streaming scenario, you probably can't afford to start off with no infrastructure. The amount of time it takes to spin up a whole new piece of hardware within your account in a cloud provider like AWS can be anywhere from 5 to 10 minutes. And so you have to request this hardware, and then you actually have to start up the software that will allow you to run that hardware or run your model on that hardware. All of that turns into a pretty lengthy process. So if you need millisecond latency, that is just far too much time. So you really are going to need to have a base amount of GPU hardware running, probably 24/7, in order to support streaming and real-time use cases. So the real savings is in how to architect a solution where the additional GPU usage that you might need for kind of periods of peak activity can be scaled up and then shut back down. So with real-time and streaming, there's not as much savings to be gained as there is with batch processing, but it can still be done. So the thing to focus on is really how to optimize the extra GPU capacity you might need. So a few options for this just-in-time GPU usage concept would be, to start looking at autoscalers, for instance, such as Kita's Prometheus, which can spin up new GPUs when needed for bursts of activity. You could also take a look at serverless inference via Kserve. That's available, I believe, I know it's on AKS, and I believe it's on EKS as well. This can launch GPUs very quickly. It has much lower spin-up time with the architecture that they've put together. And then finally, one of the last things that you can do is analyze the actual demand of your service once it's running live. You might over-provision, which means give your machine learning service more hardware than is needed in order to guarantee you're always hitting your requirements. But over time, you may see that there's really consistent patterns in activity at night, on the weekends, on holidays, during the summer. There's likely seasonality to your machine learning service that you can start taking advantage of and potentially reducing just the base amount of hardware that's running at any given time, and then turning the rest of your need into something that you scale up. And you could even preemptively scale up. You could take advantage of that time to turn things off at night, except for a very small number of GPU nodes, and then at 6 in the morning spin up one, and then at 9 in the morning spin up another. So you can take advantage of sort of your knowledge of how the business is using your model to structure things. All right, now this is where it starts to get a lot more complicated. If you have a scenario where you need to support both batch processing and real-time or streaming with multiple models, it really takes a much more complicated architecture. So rather than trying to draw out an architecture of what that would look like, I just wanted to introduce some concepts that may be useful in creating a system for supporting all of these models. So one is probably starting to introduce containers and container orchestration. Container orchestrators, you've probably heard of Kubernetes. There's a number of others as well. Docker Swarm, I think, is another one that's somewhat used. Uh, this is really the best way to manage your hardware infrastructure when you have to run multiple models that need GPUs. Simply because trying to scale up the first option we looked at really becomes untenable of having an individual queue for each model tied to one piece of infrastructure. Managing all of that becomes really, really tedious and quickly becomes kind of untenable. So a container orchestrator lets you organize and manage your use of hardware in sort of one central place, and then allows you to take advantage of that hardware for multiple models all at the same time. So that's why moving in that direction of putting your machine learning models into containers and then scaling them up or down with an orchestrator like Kubernetes ends up being really efficient because it can also do a lot of the GPU scaling up or scaling down, as well as scaling to zero that we talked about previously. But it does a lot of that for you after you put in a lot of blood, sweat, and tears yourself to set it up. Another concept that you might think about introducing is the concept of job queues, which we talked a little bit about before. But the benefit of using a queue in your solution is that it allows you to process data no matter how many GPUs are available at any given time. The queue makes sure that any requests for inference are going to be carried out, and they'll be carried out as soon as available GPUs are freed up. This is really nice because from a cost saving standpoint, you can make sure that you're packing your GPUs with data just 24/7. So that as soon as the queue for this particular model has been drained, you can shut that model down, and now that GPU is available for another model. That's one kind of challenge of GPUs, is that typically they can only run one model at a time. So you're constantly giving a GPU a model, and then as soon as it's done with its job, shutting that down to make space for another model. That's the typical operation. Now, one tip is that while that's normally the case, normally you can't share GPUs or share models. Share GPUs with multiple models. NVIDIA has introduced some new features within their A100 graphics card series that supports what's called card splitting. So the A100, I believe, can be logically treated as 7 different GPUs. So it's one giant GPU in a sense, but you can kind of interact with it in a way where it could actually have 7 different algorithms running simultaneously, and you can interact with them independently, which could be really useful. Now, those are expensive GPUs, but if you're providing support for a lot of data scientists in kind of an on-premise scenario, it could be very efficient to do that. And then finally, one of the other concepts that's probably worth considering is looking at an event-based architecture. One of the reasons why this can be helpful is that it lets you sort of asynchronously execute all of your activities, so that your GPU again is free to pick up another inference job as soon as you kind of hear that GPU is free. So again, sticking with that idea of keeping your GPUs always running, reducing the idle time, packing in the data as much as possible. Those are the kind of key elements that you want to make sure you're taking advantage of. And so one final tip here is, as you're setting up your container orchestrator, try to define multiple GPU nodes within, let's say, Kubernetes, so that you can always basically choose the smallest model available, the smallest piece of hardware that your model will run on. And that helps to make sure that you're right-sizing the hardware for the job that you're doing. Now, if all of this sounds complicated, the simple answer is that it is actually really complicated. To manage all of the hardware efficiently and cost-effectively for multiple models, to be able to support both needs for batch processing as well as real-time streaming, where you need to have dedicated hardware always running all the time, it takes a lot of work. and there's a lot of ways to do it wrong, and there's a lot of ways to end up not really getting that same cost savings. So it can actually be cost effective to go and invest in a commercial model serving platform, and that investment can actually pay for itself in GPU savings if you make the right kind of infrastructure choice. So, some tips here would be to look for a commercial platform if this is relevant to you that obviously supports GPU as well as CPU processing. Supports auto scaling, letting you define the minimum and maximum number of copies of your model that you want running at any given time. Look for something that provides scale to zero support so that you can shut all those pieces of hardware down as soon as you finished your processing. Look for something that offers custom infrastructure definition. So again, you can right size the hardware, the GPU hardware needed for your models. And then look for something that just provides general infrastructure orchestration. One great place to look for all of the commercial tools that can provide this is the AI Infrastructure Alliance. They have a really great comparison tool that you can take a look at, and it shows for I would say 99% of the machine learning platforms that offer this type of infrastructure management and cost savings, what features they offer, how they work, and you can kind of do kind of a comparison. So highly recommend checking that out. I'll share this list of references, probably both on our the YouTube channel as well as within our Discord server. So if you're interested, you can check out any of these links and kind of learn more about some of the approaches we talked about today. But hopefully, with this list of 12 options, there were a couple of practical solutions for how you can save a little bit of money on your GPU bill and your ultimately your cloud bill. So thank you so much for the time and listening in. And if you have another great tip or trick that you like to use for keeping your GPU costs low, let us know. We're always looking for other ways ourselves of keeping costs low and keeping performance up. So thanks again. Have a great day, and we'll be back with another Monty Tech Talk in late September. Take care.